in a scattering theory in quantum mechanics. From today we are going to start the different theories to explain the scattering problem in quantum mechanics. You know, there are so many methods which can be applied to discuss the problem of scattering, or particularly quantum mechanical scattering. And in this regard, first of all, we are going to see a very important method which is actually called method of partial waves or partial wave analysis to deal with the problem of scattering. Because this is my first lecture on method of partial waves. So in this first lecture, we will see only a brief introduction regarding this method of partial waves. When this method is applicable, when it is not applicable, okay? All these things we will see in this brief introduction. But apart from that introductory part of the lecture, we will also learn about a very important function which will be needed to discuss this method, and that is actually called spherical Bessel functions. Actually, I have provided a separate video on this spherical Bessel function in my playlist Mathematical Physics. You can also watch my videos on Bessel function in Mathematical Physics, particularly in the chapter Special Functions. But as here we will need its application in dealing with the problem of scattering in quantum mechanics, so I would like to acquaint you with this very important function first of all, because it will be needed at different steps in our calculation. Okay, so this lecture is intended to discuss two aspects. First of all, we will see a brief introduction, and after that we will learn something regarding the spherical Bessel function. Actually, as I am just reminding you this function, so I will not make any detailed calculation, but I will refer some important results which you will have to remember for your study of a scattering problem. Okay. So now let us see what is this method of partial waves or partial wave analysis to deal with the problem of scattering. In fact, you know, whenever a scattering takes place, as I have discussed in my previous videos, that in any scattering experiment, there is a target on which the incident beam of particles are incident. And that target is actually, in terms of quantum mechanics, a source of potential. And that potential, which is also called a scattering potential, that potential actually produces a scattering to the incident particle. So the nature of potential plays a very important role in a scattering problem. And what type of potential you are using for the scattering process, that actually decides which method will be applicable. So when you talk about the method of partial waves, then you should know that this method can be applied only when the potential is a central potential and it is of finite range. It means the partial wave analysis is applicable in case of the scattering potential which is central in nature, or spherically symmetric, you can say. And apart from that, it should be also of finite range, not of infinite range. For example, you know about Coulombian potential, that Coulombian potential V of R is given as some constant over R. And you know, this potential will V of r will tend to 0 when r is tending towards infinity. So this Coulombian potential is of infinite range. So you can say that method of partial waves cannot be applied in case of Coulombian potential, okay, because it is of infinite range. But if the potential is of finite range, it vanishes after a certain distance from the scattering center, then this method will be applicable. And you know, when you talk about central potential, that potential depends only on the position vector or the magnitude of the position vector r. Okay, so when v of vector r is equal to simply v of r, then you say that potential is central. And when you talk about that the potential is of finite range, what does it mean? It means this potential v of r vanishes, it becomes 0 for a definite value of, after a definite value of r. It means if you consider that this v of r is non-zero when r is less than r naught, but it vanishes, it becomes 0 when r increases from this r naught. So this r naught is also called the range of this potential, because after this potential vanishes. Okay, so this is the most remarkable fact. If a question in objective type is asked to you, when you apply the method of partial waves, the answer will be when the scattering potential is of central nature, or it is a central potential or a spherically symmetric potential, only then you can apply this method. Okay, and this potential also, you know, Coulombian potential is also a central potential, but it is not of finite range, it is of infinite range. Okay, so these are the condition that potential, if the potential is central, we can apply this method. This is not 100% correct. Apart from that, you have also to say that this potential must be of finite range, not of infinite range. Okay, now the method which we will imply to discuss the scattering problem, that also depends on the energy of the incident particle, that is energy of the projectile. So you have studied in my videos in nuclear physics different type of a scattering problem, and there you have seen that when the incident particle has low energy, high energy, the nature of a scattering changes. Actually, if you talk about the method of partial waves, this method is applicable only when the energy of the incident particle is low. It means if the incident particle has very high energy, this method will be not applicable. We will see in my forthcoming videos a very important another method, that is called Born approximation. You will see that if the energy of the incident particle is large, not very small, then this method of partial waves fails, and we apply an approximate method which is called Born approximation method to discuss the scattering problem. So remember this another fact too, that partial wave analysis will be useful, will be advantageous, or will be applicable in case of the incident particles having low energy. Okay. Now you have definitely studied the concept of central potential, particularly in case of your course on classical mechanics, and I have also provided so many videos on this subject of central motion in central force field, and there you learn that if the potential is spherically symmetric or the potential is central, then the angular momentum of the particle moving under that potential remains constant. So the angular momentum is a constant of motion for the particle moving in a central force field. So in this case you can say that if the particle is incident on the scattering potential, which is either a spherically symmetric potential or a central potential, then its angular momentum, and you know in quantum mechanics angular momentum is defined like this. This is a square root of a small l times l plus 1 times h bar, where L, you know, this is orbital quantum number, and this capital L represents the angular momentum. So in this case, this angular momentum of the scattered particle will be a constant of motion. This is a very important property of the central force field. Okay, and I hope you have an idea of this. Now, since the angular momentum of the scattered particle will be a constant of motion when the potential is central, this fact actually is very advantageous to develop solution in terms of angular momentum eigenfunctions. Okay, and if the potential is sufficiently of short range, okay, or energy of the incident particle is very low, then it will turn out that only a few eigenfunctions with a small angular momenta, that is only a few partial waves, will really be affected by the potential. So in this case, a small number of particles will be affected, and we simply say that a small number of partial waves are really affected by such a potential. Okay. Now, as you have seen in my preliminary videos on this scattering problem earlier, that when the particle is incident on a target, we then consider that these particles have linear momentum, which is given by h bar times k, where you know this k is the wave vector. Okay. So if you assume that the incident linear momentum, which is h bar times k, assuming that the incident linear momentum h bar k, large angular momenta correspond to large values of impact parameter. Okay, and the particle is hardly deflected, because if you consider that the incident particle which has linear momentum h bar k has large angular momentum, corresponding to the large angular momentum, the impact parameter of the collision will be also very large. And if the impact parameter is large, then the deflection will be, the probability of large deflection will be very small. And so in that case, the particle is simply passed through the potential field undeflected. So I have written here that particle is hardly deflected. Okay. Now, if you consider that the range of our potential is A, then angular momentum, which is given by this expression, with L much smaller than k times A. Okay. Now, you have learned earlier in my previous video that the incident beam of particle is represented by a plane wave, that is e to the power I k dot r. This is actually our incident beam of particle, because we consider the incident beam as a plane wave. Now you know a plane wave is characterized by a definite linear momentum, which is given by h bar k, but no definite angular momentum. This is a very important property of the plane wave. A plane wave has a definite linear momentum, but not a definite angular momentum. In fact, whenever you talk about the plane wave in at least in principle, this is of infinite extension. Okay, and if you consider that the plane wave is of infinite extension, then actually this corresponds to impact parameter varying from 0 to infinity. Okay, and if the impact parameter will vary from 0 to infinity, correspondingly the angular momenta content in a plane wave will also vary from 0 to infinity. Okay, and that's why it is possible to analyze a plane wave into an infinite number of components, and among those components each will have a definite angular momentum. Now actually each of such components is called partial waves. Okay, and the process by which you decompose a plane wave into its component, that is partial waves, that is actually called the partial wave analysis or partial wave method. Okay, so these were some preliminary important facts regarding this method of partial waves, and I hope you have definitely understand this basic concept of this method. Okay, now as I have told you earlier that for discussing the proper theory of partial waves, we will need a concrete knowledge, a concrete idea of a very important function of mathematical physics, which is called spherical Bessel functions. And I will suggest you, if you want to understand each and every aspect of my forthcoming videos, you must have a concrete knowledge of Bessel function. So I will suggest you to watch my videos in the playlist of mathematical physics on this Bessel function. Okay, particularly the spherical Bessel function will be used in this theory. So before going through the rigorous theory of this partial wave analysis, I am presenting here some of the basic facts regarding this spherical Bessel functions. Okay, and this discussion is just limited to some aspect which will be needed in our problem of scattering. Okay, so I am not teaching you spherical Bessel functions in very detail, but I am just giving you some informations regarding this which will help you to understand the concept which will be dealt in our forthcoming videos. Okay, I hope you have a concrete knowledge of Schrodinger equation in a spherical polar coordinate, particularly when you study the problem of central potential in quantum mechanics. For example, you have definitely studied hydrogen atom. Then you have definitely seen that actually the Schrodinger equation, which is set up for a particle moving in a central force field or under a central potential, then the equation has actually three parts. First one is called the radial part of the equation, another is called angular part, and angular part has actually two parts. First one is called theta equation, another is called azimuthal equation or phi equation. Theta equation is also called polar equation. So actually Schrodinger equation has three parts: radial part, okay, the polar part, and the azimuthal part. Now when you talk about the spherical Bessel functions, the idea of this function in terms of quantum mechanics can be found in terms of the radial part of the Schrodinger equation, when this equation will be written in a central force, in a central potential. Okay, and I hope you can definitely remember that expression. So I have written here in this equation 1 the radial part of the Schrodinger equation, only the radial part. And this equation reads as 1 over r squared d dr, r square times dr by dr plus 2 mu over h bar square e minus v of r minus L times L plus 1 h bar square over 2 mu r square times r of r equal to 0. Actually here this mu is actually the effective mass of our system. Okay, and inside this square bracket, E is the total energy, V of R is the potential energy, and what is this third term? Definitely you have an idea. This is actually called centrifugal potential. Okay, this is called centrifugal potential. Now this equation which I have mentioned in equation 1, which is actually the radial part of Schrodinger equation, I would like to cast it in a convenient form, and for this we make these two substitutions. If you consider that rho is equal to k of r, k times r, and where k is this much, 2 mu e over h bar square whole to the power half. Actually, when you will use these results in equation 1, then this equation 1 becomes like this. I have not done the algebra, you can check it. You can find dr by dr, okay, and you can replace this 2 mu r square from here, okay, and after doing all those algebra, you can see our equation 1 becomes like this. This is 1 over rho square d rho operated on rho square dr by d rho plus 1 minus L times L plus 1 over rho square r of rho equal to 0. Actually here we have also considered that our particle is free, and in case of a free particle, the potential function V of r is 0. Okay, this is a common fact. So we consider a free particle for which this V of r will be 0. Okay, and after that we make these two substitutions, rho equal to k times r, and where k is this much. So after this, our equation number 1 becomes as you can see in equation number 2. In fact, this equation 2 which we have obtained here, this equation is known as a spherical Bessel equation. This equation is called a spherical Bessel equation, and this is a second order differential equation, so at least there will be two independent solutions of this equation. And the solution of this equation are known as spherical Bessel functions, and these spherical Bessel functions are denoted by the symbol small j L of rho and n L of rho. These are actually the two solutions of this differential equation defined in equation number 2, which is called a spherical Bessel equation. Okay. Now, if you will make a transformation, let us say r of rho equal to u of rho over rho. Actually, our aim is to cast this equation in a most convenient form, in the form of a standard differential equation. And you also take the situation for which this L is equal to 0. So after taking L equal to 0 and making this transformation, r of rho equal to u of rho divided by rho, then this term here, the first term, you can check what will this now become. So now I am going to find the value of this under this assumption that r of rho is equal to u of rho over rho. You can see this is 1 over rho square times d rho rho square, okay, and dr by d rho. But r you have assumed is equal to u over rho, okay. So let us differentiate this u over rho with respect to rho. This will be 1 over rho times du by d rho minus 1 over rho square u rho. This is just a product of two functions. One is u and another is 1 by rho. Okay. And so this becomes 1 over rho d rho. Now multiply by this rho square to the terms inside this bracket. After multiplication, you can see this is rho times du by d rho minus u, or u of rho. Now let us differentiate the two terms inside this square bracket. You can see this will be equal to rho times d2u by d rho square plus d rho by d rho will be 1. So this is du by d rho and minus du by d rho. So this two term will cancel out, and finally we see that 1 over rho square d rho square dr by d rho, this is equal to this much. Okay. Now if you consider that L is 0, so for L equal to 0, now this equation 2 will become what? You have already obtained the value of this much, which is actually independent of L. And when you will take L equal to 0, this second term, which is the centrifugal potential, this term will vanish. Okay. And this R will be equal to U over rho. So making these substitutions in this equation 2, now this equation becomes 1 over rho times d2u by d rho square plus u of rho over rho equal to 0. Now this if 1 over rho is not equal to 0, or you can say rho is not equal to infinity, actually then our equation becomes d2u by d rho square plus u rho equal to 0. Now see the form of this equation. Can you remember that this standard differential equation in physics comes at several places? This is nothing. This is simply the equation of SHM, because if you talk about the linear SHM, you write equation in this form: d2x by dt square plus omega square x equal to 0. Here the quantity x is oscillating with angular frequency omega, and this oscillation is in terms of time. Okay, so this is oscillation of x with respect to time. Here there will be oscillation of u with respect to rho, and at the place of omega square there is 1. There is 1. So you can say that this represents a simple harmonic oscillation of the quantity u with respect to rho with cyclic frequency unity. Okay, and you have definitely an idea that the solution of SHM, solution of the differential equation of SHM contains can be written in terms of sine omega t, in terms of cos omega t, in terms of e to the power I omega t, and so on, and a combination of sine and cos. Here omega is equal to 1, and at the place of t you can see there is rho. So you can easily say that the solution of this very equation 3 will be sine delta and cos delta. I have not written the constant factor multiplied to it. Okay, and that's why when L is equal to 0, then the two independent solution of this equation 3 is written like this. This is J0 rho. Here 0, the subscript 0 is at the place of L. So J0 will be equal to 1 over rho sine delta. And N0 rho, this is the another solution, that is 1 over rho cos rho. These are actually the zero order Bessel function, a spherical Bessel function. Okay. Now, In general, the solution of Bessel equation is called Bessel function. This is a spherical Bessel function. So how the spherical Bessel functions are related to the Bessel functions? I have written here. You can see this JL of rho, this is a spherical Bessel function. Okay. And this JL plus half of rho, capital J, this is only Bessel function, not a spherical Bessel function. And this spherical Bessel function, a small jl of rho, is related to the Bessel function jl plus half rho by this relation. So jl of rho is given by a square root of pi over 2 rho times the Bessel function jl plus half of rho. Okay, I have actually written this result directly without any proof, because in the beginning of my video I have told you that our aim is only to know about some of the facts which will be needed. Our aim is not here to deal with the problem of Bessel function in very detail. That is the subject matter of our course in mathematical physics, and for that you can watch my videos. Okay. And this NL of rho, this is equal to minus 1 raised to the power L times a square root of pi over 2 rho times J minus L plus half of rho. Okay. I will suggest you must remember these two results. Okay. These two results you must remember. Now, we have already seen the expression for the zero order spherical Bessel function J0 of rho and N0 of rho. Now, using the expressions for J0 of rho and N0 of rho, we can calculate the higher order functions, but that higher order functions can be obtained in terms of the two important recurrence relations. When you will watch my videos on Bessel function in mathematical physics, you will see that there will be a set of recurrence relations or recurrence formula which is obeyed by this Bessel function, and there you will also find the proof of those recurrence relation. But I have mentioned here two recurrence relation directly, and you have to remember it. The first one is JL plus 1 of rho is equal to L over rho times JL of rho minus J dashed L of rho. What is this J dashed? Here dashed represents the first order derivative. Actually, J dashed L of rho means d rho J L of rho, not J rho, JL of rho. And similarly, this NL plus 1 of rho, this is equal to L over rho times NL of rho minus N dashed L of rho. Similarly, here this N dashed L of rho means d rho NL of rho. Okay. Now, you have already seen that J0 of rho is this much. Now, using this recurrence relation, when you will try, I have not done the algebra, you can see, when you will try to find J1 of rho, and for this you have to take L equal to 0, and then you will see that J1 of rho is equal to 1 over rho square sine rho minus 1 over rho cos rho. When you will differentiate it, this will be cos rho over rho. So this second term will be equal to 1 over rho cos rho. Okay. Similarly, if you try to find J2 of rho, then this will be 3 upon rho cube minus 1 over rho sine rho minus 3 over rho square cos rho. And in this way you can obtain the higher order spherical Bessel function. And in the similar manner, utilizing this recurrence relation, you can find the value of the higher order Bessel function NL plus 1 of rho. Okay. Actually, this N0 of rho already you have defined earlier, and using this formula you can see N1 of rho will be equal to this much. This is 1 over rho square cos rho plus 1 over rho sin rho, and N2 of rho will be this much. Okay. Now, in fact, in dealing with the problem of scattering, we will have to see the asymptotic form of this spherical Bessel function JL of rho and NL of rho. When you talk about asymptotic function, it means when this rho will tend towards infinity. Actually, when this rho will tend to infinity, then JL of rho is given by this expression, 1 over rho sine rho minus L pi over 2, and NL of rho is given as 1 over rho cosine of L rho minus L pi divided by 2. Okay. So these were some basic facts regarding the spherical Bessel function, and I hope you will remember these things, because I have not discussed it in very detail by the proper calculation, because this is just a knowledge for you which will help you to understand the concept of method of partial waves, which will be discussed in my forthcoming video. Okay, thank you very much.